Okay, good. So, all right. So, okay. So it's my pleasure to welcome Suresh Jagannathan. I hope I pronounced it correctly, from Purdue. So Suresh is a professor, full professor at Purdue University, and he got his PhD from MIT. So Suresh has done a lot of important and fundamental work in program analysis, in learning, in specification learning, in learning invariants, and he will tell us today a little bit about this line of work. So please go ahead.
Yeah. Thanks very much, Martin. So I'd like to talk today about some ideas that we've been exploring for the past few years on trying to learn specifications. And the problem is very simple. I give you a program, and can you tell me what the program is actually doing in a form that is understandable to users? That problem in and of itself is quite simple. The challenge that I think makes it intriguing and worthy of investigation is trying to make sure that the things that you actually claim the program is doing can be verified, are actually sound, are actually true. So this notion of trying to relate the notion of specifications to some soundness properties, some safety properties, is what I think makes for some interesting technical challenges that I'd like to talk today about. So here's the setup. I have a program, and I want to be able to verify this program in some way. And the way that I'm going to be able to verify it is by having some specifications that define ground truth in some sense of what the program is doing. And I might write these specifications in a number of different ways, types, loops, assertions, contracts, what have you. But the problem is that in general, you need some guy sitting there who's actually going to figure out what those specifications are. And so what we're interested in is to see whether we can get a machine to do it for us. Now, this is a bit facile. I mean, clearly, the machine can't be expected to learn ground truth automatically. So, yeah, there may be a little bit of help, but we want to sort of minimize the amount of intervention that the programmer actually needs to provide in order for us to be able to generate these specifications. And because our ultimate goal is to do verification, we want to make sure that these specifications are in a form that actually lends itself to proving interesting properties or to verifying the correctness of the program at hand. Okay, so the way we're going to do it is by applying learning. And I'm using learning in a very loose sense. So, it could be machine learning. I might throw deep networks or some other thing like that at this problem. But it could be other forms of learning as well. And there are many, many different techniques, many, many different styles of learning. And we're quite agnostic to which ones we choose. So I'll talk about a couple of different strategies that we've adopted to actually addressing this problem. So, just to sort of set up the stage here, the idea is that we first need to figure out what it is that we want to specify, and we're going to call this sort of domain the concept class of the problem that we're interested in. So maybe I want to reason about data structures. I want to reason about the heap in some way, or maybe I want to reason about specifications that have to do with loop invariants, or maybe I want to reason about properties that deal with concurrency. All of those define some sort of concept class, the space in which I'm going to apply my learning techniques against. And what I want to do is, from a program, I want to be able to extract features that are going to be relevant to this concept class. So think of a feature as a set of predicates, a set of atomic predicates that are going to define the kinds of things that I can actually specify over. So these are the building blocks for the language that's going to define the specs that I'm going to build on. And those features, collectively taken together, are going to fit within the sort of space of all specifications that I can build. And we'd like that space to be reasonable. We don't expect it to be complete, right? Because there's an arbitrary number of things that I might want to be able to prove, and we can't assume that we can prove all of them. But we'd like that blue thing, that blue circle, to be interestingly large enough that we can actually show the kinds of things that most programmers are interested in. And then we're going to look at the program. And the way we're going to look at the program is we're going to run it. We're going to we can think of the program as a black box, or maybe it's a white box, but we don't really care right now. What we're going to do is we're going to sample the behavior of the program in some way, and then we're going to try to see whether we can match the behavior that we see to the feature space that we've constructed. And if we can do that effectively, then we have a form of specification inference. Now, in this picture, I haven't talked at all about verification or anything. So there's things that need to get filled in here that actually tie all of this into the sort of general goal of relating this to a program verification problem. So this particular idea of specification inference via learning in itself is not new, and there's been a whole bunch of work, some of which has actually been done here, and instead of going through all of the details about what these different results have been, I think it's better to sort of abstract things out a little bit and ask the kinds of questions that any purported system that claims to do specification inference has to address. So here's one question. What is that concept? What is the concept class? What does the feature space that's defined over this concept class actually look like? How do we actually write down these specifications? How rich can they be? And if we're too ambitious, maybe we get a very, very rich specification language, but we lose decidability. We can't do anything with it. So there's a game that we have to play here to balance out expressivity from actual decidability and provability. How do we actually generate samples? We could imagine that we could just run the program using random testing, and maybe that works, but it's not at all clear that that's going to be effective. So do we have a more principled strategy that we can use to actually generate the inputs that we need and to get interesting outputs that can actually drive a learning algorithm? How do we generalize from samples? So clearly, just doing sampling is a gross under-approximation of the actual behavior of the program. So we can't imagine, it's hard to imagine that just by running the program a couple of times, or n times, or maybe even 100 times, that we're going to get enough information just from that to actually produce a specification that's actually sound in some sense. So what is the mechanism by which we generalize from the samples that we actually collect to something that could actually be shown to be a valid, safe characterization of what the program is actually doing? And since we would like to automate this pipeline as much as possible, we want to make sure that the specifications that we generate are inductive in some sense, that they can be discharged using existing automated tools, SMT solvers and proof assistants, things like that. So relating the quality of the specification to things which can be automated leads to another set of questions on the expressivity of the kinds of things that we can build. How do we know that if we run our sampler 10 times and we get something and it's not good enough, how do we know that if we keep running it that we'll actually get better? So is there a notion of progress that can be formalized that relates the amount of time that I actually try to learn with the quality of the specifications that I actually produce? And related to this question is, how do I know that if I run for an arbitrary amount of time, or arbitrary long amount of time, that I'll actually converge to producing a specification which is inductive and safe and sensible? So all of these tie into this question of what is the quality of the specifications that we actually produce. I could imagine generating specifications that are as big as the program itself. That's not particularly useful, and it's probably not going to be very valuable for verification, because the harder the specifications are to reason about. If it's hard for humans to reason about, it's not that clear that it's going to be easier for machines to do anything with. So we want to sort of qualitatively think about simplicity and minimality in the kinds of specifications that we build. Okay, so that is the sort of wish list of the kinds of things that we want. So what I'd like to do now is sort of give you two examples of experiments that we ran, two particular instantiations of this idea. So the first example is, if I give you, say, an OCaml program, can you actually infer interesting specifications about data structures? So how do I know that, say, a tree is really balanced, or that when I rotate a red-black tree that I maintain the red-black property without actually writing it down? Can I just sort of observe things and figure that out for you automatically? So that's going to be one experiment. And then the other idea that I'll look at is something more traditional. Can I actually use learning for actually discovering deep loop invariants in programs so that I can actually verify numerical programs in a fully automated way without having to actually generate loop invariants internally? Okay, so Here's the first idea. So suppose I give you a very, very simple program. It's got lists in it, it's got trees in it, and maybe the program that I want to do is to take a tree and turn it into a list. Okay. So here's a very simple program, and the code itself is easy to understand, but all it's doing is it's constructing an in-order traversal of the tree, and it's producing an output list. Okay, that reflects that in-order traversal. Right. So the interesting thing to note about this particular program is there are no assertions, there's no postconditions, there's no loop invariants, there's no contracts. But if you and I looked at it for a little bit and we ran a few tests, we would probably figure out that it's doing what I just said it was doing. And indeed, if I were to run some tests on this code, we would see that the way that the program traverses the tree corresponds to the way that the code is actually emitted in the list, right? So it's doing an in-order traversal. So here's the specification that I, as a tester, would probably have come up with. And I don't write it down anywhere, but if I look at the program, I would have figured out that, yeah, the in-order traversal of the tree corresponds to the forward order traversal of the list, and that these two things are the same. And that's my spec. That sort of is a reasonable characterization of what this program is doing. So now the question that we want to ask is, okay, given that that's what we would like to achieve, what is it that I need, given what I said before about feature spaces and concept classes and stuff like that, to actually generate that automatically? So here's what we're going to do. So as a starting point, pretend that we will develop a feature space for this program, or for this language, for ML, that lets me reason about membership and containment and order in these data structure programs. And this is illustrative, but you can imagine adding other kinds of predicates. But the predicates that I've listed on the left sort of capture the sort of core things that we need to sort of show for this example. And I'll talk later on about how we can go beyond that. So the notation T dashed arrow U says that I have a tree T and it has an element U, right? The right angle arrow says that I have a tree T and it has a node U, and this node happens to be a root node of a node V, which is in the right subtree of U. And conversely for the left angle, so U is a node that's rooted at a tree which is in which there's a node V, which is in the left subtree of that node. And then the curvy arrow says that I have two nodes, U and V, and they occur in two different subtrees where U is in the left subtree, U is left of V, right? So things like that. These are predicates that define ordering properties on elements in a tree. And conversely, and similarly, for a list, I might have things that says, okay, if I have a list and U occurs before V in that list, then we'll write that down with that predicate that defines that right arrow. Okay, so this is very, very simple. So now the question is, given this little program, can I actually construct the specification? Can I actually combine, using some combination of logical connectives, a particular specification that sort of matches up? And if I could do that, can I sort of automate this whole process to make sure that this thing is inductive and can be generalized and so forth and so on? So here are sort of simple examples of what the different kinds of relations that we've built actually look like, and they're all fairly standard, right? Nothing particularly profound here. So, given all of that, on one hand, I've got a tree. And I have a function that's going to produce a list. And so I can sort of lay out all of these predicates on one side, which is my inputs. And I can lay out the predicates that correspond to the output data type. And then the goal here is to sort of figure out a classifier, right? So now I've got a whole bunch of different choices. And so the learning question is, can I cull out, given this large set of possibilities, something that looks much smaller, right? And if I could do it, then we've done something which essentially extrapolates from what the programmer would have ordinarily done just by testing into something that could actually be used for verification. Okay, so if you sort of run our algorithm, you'll get something that looks like this. It'll say that for any pair of nodes, U and V, if the tree that we're operating on, that belong to some tree, it is going to always be the case that if either U is in the left subtree of a node rooted with V, or U happens to be a node that sort of sits below a node that's in the right subtree, or that U and V sort of have this left-right subtree relationship, then U will occur before V in the tree, and this is a by implication. Okay. So these are the sort of different steps that I just sort of mentioned. Okay, so now the first question we want to ask is, I gave this little example of these trees and properties like containment and all. How do I actually, where did that come from, right? I may have made it up, but that's not particularly satisfying. So the question is, can we actually extract these features automatically? And interestingly, these features are inductive in the sense that they sort of operate over any arbitrarily shaped tree. So presumably, that information is latent in the actual type definition that we actually see. So for example, if I stared at this type, it's clear that there's a relationship between the value of at a node and its children in some sense, right? For example, I know that the node that it gets instantiated to code A, the value that gets instantiated to code A is always going to be in an ordering relationship. It's always going to maintain an ordering relationship via this left angle guy with any element that sits in the tree represented by in the left subtree, and conversely, it'll share this right angle property, this right diagonal arrow property, with anything on the right subtree. So one thing that we can do immediately is imagine extracting the features that we want just by the shape of the inductive data type definition that we have. So it's not the case that the programmer has to figure this out. We can actually do this automatically just by reasoning over, as long as the concept class that we're interested in is data types, and the properties generally have to do with containment and ordering and things like that. The specific characteristic of what that means can be extracted from the definition of the data type itself. And indeed, right, we can generalize what we actually mean when we say that that V is in the left subtree of U by expanding out properties of the data type definition according, in various ways. So this large formula sitting on the bottom, which is not that particularly interesting, just extrapolates formally what we mean when we say that one node is in the left subtree of another node. Okay. Right. So one thing that we can do then is we can sort of generalize all these different predicates, and we can encode these predicates in these kinds of formula, right? So we can get features. So now we have in our hands a collection of features that all relate to ordering and containment that have been extracted from the data type itself. But that doesn't help us very much, because the whole name of the game here is to try to actually learn this combination. So here's a really simple idea, and we'll see how far it works. So the idea is, let me just very naively enumerate over all of the possible features that I have over trees, right? And that's my input, because my function takes a tree as its input. So all of these things here in blue represent possible features that may occur. And let me, for every possible feature in the output, which is a list, consider the relationship between these two things. That is, whenever a feature holds in the input, does it hold in the output, right? And the way that I'm going to do this is by just sampling. I'll just generate a bunch of trees, right? I'm actually going to do the one thing that I said that I said probably won't work, which is just run a random test generator and generate inputs, right? And then look at the individual elements in the trees that are produced and see how, and then see whether it holds or not. So for example, if I give you a tree in which 1 is the leftmost leaf and 2 is its parent, right? We can sort of look at the different instances of the properties that we have to actually see which properties are relevant for producing a valid output output claim. So what is the output claim? So the output claim for this particular sample says that 1 must occur before 2 in the output list, if I read the list left to right. And this particular entry here says, indeed, it is the case that 1, indeed it is the case that 2 occurs before 1 in this left tree ordering. 2 does not occur, 1 does not occur before 2 in the right subtree, and so forth and so on, right? Now, bringing back our sort of elementary school reasoning on truth tables, right? We have a truth table here, right? It's a bunch of features and a bunch of with inputs and outputs, and so our goal is to try to see whether we can build a simple classifier just using this truth table notion. Now, I have very, very carefully constructed this particular ordering so that it all looks like the first samples all seem to be 1, and the second samples all seem to be 0. And so the classifier that we can generate is actually very, very easily discerned from this, right? We just need to read off this table and look at where all the 1s occur, right? And if we can do that, if we just read it left to right, every place there's a 1, well, that represents a signal. Things that are 0 represent things that are not interesting. And so we can essentially build a truth table that sort of says that when run, produces the exact same specification that I said before, right? And the goal here is that we just want to make sure that anything that's in the, any positive sample is represented or is covered by the specification that we produce. And we don't include in the purported specification anything which is in the negative, which is included in the negative sample, right? So the sort of 0th order proposition here is that we can define a classifier. Now, if you just look at this problem or think about this problem just for a little bit, you should have doubts whether this is actually true, because if it was as simple as always defining a classifier over this, then where's the interesting problem, right? So, and indeed, while we can do this on while we can sort of imagine doing this for some problems, the fact that we have no other thing to hold on to other than the input-output behavior of the program leads us to suspect that there will be instances where, in fact, there is no such classifier. There is no simple way to separate out these features. Why? Well, there are 2 reasons. One, maybe my feature space is in fact too impoverished to sort of differentiate between the samples that I've actually given, right? I made no claims that the particular choice of these predicates that I constructed were in some sense complete or sufficient for all the kinds of problems that I might want. That's one thing. The second problem is maybe I just didn't sample enough. Maybe my sampling, just doing this random testing strategy is biased. And so I didn't get the information that I needed in order to be able to actually partition the space appropriately. Right, so, right, so anyway. So let's hold that thought. So here's what happens when I build a truth table and I get the specification that I wanted. Okay, so the general question that we want to ask is, are we sure that we'll always be able to build a classifier? So here's an example where I haven't given you sort of the details of what these features are, but imagine that I generate for a given program a set of samples, and if we look at the first row here, we find that the output, that this is a positive sample, say, and its input feature 7 and input feature 4 happen to be true. Here's a negative sample, right? And here we find that input feature 7 and input feature 4 are also true. So it is conceivable that we can generate examples where we have both positive and negative samples that have the same structure in terms of their input features. So the question is, when we have cases like that, this sort of first order strategy of simply partitioning the space accordingly to, partitioning the space cleanly doesn't work. Right. Okay, so what do we do? Before I tell you what we do, let me give you a concrete example to say how this shows up in practice. So here's a very simple program that's that's inserting nodes into a binary search tree. So you can imagine that I could have a tree that looks like this. So it's got a node that has 4 in it, and a smaller value 2, which occurs on the left subtree. And now I want to insert 3. Right? So without reading through the code, just believe me that the shape of the tree that I get as a consequence of applying this function looks something like that, right? So 3 is on the right subtree of 2 because it's bigger, but it's still in the left subtree of 4, right? Okay. So I can imagine doing exactly the same thing that I did before. I have a bunch of input features and a bunch of output features. And unlike before, where the output features were drawn over lists, here the output features are over trees again. And I'm just showing you one particular output feature that I'm going to postulate as a particular specification, as a particular kind of thing that I want to pivot against. But you can imagine doing this for all the other kinds of output features all the other kinds of features that we have over trees. But for the particular case that we have here, the sort of output feature that I'm going to think about is the feature that relates nodes based on the sort of left subtree property. So here's an example. So I might imagine running, just looking at the input, I might ask, well, okay, under this particular structure, tell me what the input-output truth table looks like for 4.3. And we see here that indeed pi 6 holds for 4.3, and pi 6 says that 4 is included in the tree, right? Pi 9 holds, right? And pi 9 is something that says the thing that I'm inputting in is 3, so that holds here, right? And I can do something for 2.3 as well, and so forth and so on. Except that when I look at 2.3, which is a similar thing, indeed 2 occurs in the tree, right? And indeed, the thing that I'm inputting in is 3, right? But clearly, with respect to the output feature, right, 2 is not in the left, 3 is not part of the left subtree of 2, whereas 3 is part of the left subtree of 4. So here's an example where we've got samples. The feature space is insufficient to differentiate between them. So we have to come up with a way of figuring out how to separate samples that are inherently non-separable given the feature space that we've got. Okay. Right. So we're going to apply a very, very simple algorithm. So when we have coincident samples like this, we are simply going to break the if and only if into an if and an only if. And what this means is, if we think of if as reasoning over positive samples, we're going to essentially we're going to strengthen our understanding of what positive samples mean with respect to a specification. And if we think of only if as reasoning over negative samples, then we're going to weaken what we mean by what a bad sample actually is going to be. So without belaboring the point, intuitively, what this means is that we can eliminate the violating positive sample and then try to analyze what the meaning of a specification would be, assuming that we want to satisfy the output specification. And if we sort of stare at this a little bit, we observe that if we want to claim that V occurs in the left subtree of U, it is sufficient for us to know that V occurs in the left subtree of the input. V occurs in the left subtree of U in the input, right? So that's a sufficient property that would satisfy this particular spec. And conversely, if I sort of eliminate the violating negative sample, I can observe that if I know that U shares a property with V in the output, according to this left tree diagonal, then it's enough for me to know, again, that it shares that property in the input, or that there's some membership relationship in the there's a membership relationship on U and V in the input structure. Now this is a weaker property than we had before, but interestingly enough, it satisfies the requirements that we need in order to be able to sort of show the notion of what insertion is. So a safe insert property means that we must preserve the shape of the input and the output. That's really what we're trying to get at. And that comes out by essentially conjuncting these two particular specifications. Right. So I have a bunch of specifications. We've applied some algorithms to try to ensure that even if we can't separate them with a single classifier, we can generate a family of classifiers to separate them. But how do I know that these specifications are actually sensible? I've tried to argue in words that they are. Can we automate this process? So one of the things that we tried to do is to enforce, is to ensure that we can construct an automated procedure to do this. And the way we did it was, since we're operating inside ML, we used types. Right? In particular, we integrated this entire specification inference engine into a liquid types framework. And we essentially encoded all of these specifications as part of the EPR fragment supported by Z3. And we augmented liquid types to sort of do the heavy lifting to ensure that pre and post conditions on these specifications actually hold. So if I claim that a particular specification holds for a particular function, then I use liquid types to ensure that that property is guaranteed at call sites to that function, and conversely on returns as well. Right? So I'm not going to go through the rules here, but the notable part of this particular slide is that for each particular data type that we generate, we instantiate specialized rules that allow us to reason over the particular the particular forms of containment, membership, so forth and so on, that are necessary in order to be able to discharge the subtype the subtype check that liquid types requires in order to guarantee safety. The consequence of this is that in order for liquid types to work, all of these rules, all of these specifications that we generate have to be inductive, right? Otherwise, that particular check would fail. So coming back to our original question, how do we know that we've got an inductive type or that we can do our verification? Well, liquid types is going to do that work for me, right? So we encode our specifications in a form that guarantees that it's inductive simply because it won't pass the type checker otherwise. So here's the sort of setup that we have. So given an arbitrary OCaml program, we do feature extraction over the data types that exist. We apply this learner that I sort of intuitively talked about. And this learner does two things. It'll either give me an inductive specification, because in order for this to work, it's going to have to pass the verifier, which in this case is Z3 and liquid types, or it's going to fail. Right? It's going to run, and if it's not able to discover, a specification that's satisfiable, then we can actually claim that our hypothesis space is simply insufficient to satisfy the requirements that we need. And we just sort of repeat and rinse and repeat. So one might argue, one might ask, what kinds of claims that we can actually make here. And the sort of most interesting claim that we can make, which I think is a very powerful one, is that we can prove that the algorithm that we've got will in fact always produce the strongest inductive invariant for the feature space that we've actually generated. So this in fact is progressive and convergent. The only thing that blocks convergence is if the feature space that we have is in fact irrelevant or impoverished with respect to the programs that we're operating on. But experimentally, interestingly enough, it seems to work extraordinarily well in practice. So for those of you who are familiar with Okasaki's benchmarks, these are very elaborate, very performant benchmarks that have been written for functional data structures. And this particular framework that we've got has been able to sort of prove all of them. And it's been able to, with some slight extensions, to deal with things like measures, numerical properties over programs like balance and height and things like that. We've also been able to sort of show deeper properties, like, for example, that in a skew heap, the maximum difference between the right subtree and the left subtree in the heap is no more than 1, right? So all of that sort of is generated automatically. And the kinds of specifications that we produce are non-trivial, right? These relate to balance properties, reversal properties, heap removal properties, various kinds of shape data, and so forth and so on. Okay, so this is sort of one idea. Let's just use a combination of specifications extracted from inductive data type definitions along with random testing to sort of build conjunctions of classifiers that can actually produce interesting specifications that are verifiable. So in the time that I've got left, let me talk about a sort of a different idea. So here, we're going to say, let's not worry about functional programs. Let's just look at classical C programs and see if we can do the similar kinds of things, except that we don't have types and we don't have the richness of liquid types or things like that to help us. So we're going to have to sort of take a different strategy. So here's sort of an introduction to this question. Here's a really simple program, right? And it's just iterating over variables x and y. This is the control flow graph for this particular program. If I apply this program over over standard verifiers, constrained Horn clause logic solvers, I might generate a bunch of verification conditions, right? One verification condition might tell me something about the inputs, right? That initially x has to be 1, y has to be 0. There's another condition that talks about the actual structure of the loop itself. And the thing to note here is that there's this predicate p, which is unknown, which is the loop invariant that we're trying to reason over. And this particular formula tells me something about how the loop iteration operates on entry to the function. Here's another invariant that sort of talks about what happens during the true branch when I execute the true branch, that we increase the value of x and y by some property, by some value. And the last condition tells me something about the fact that the assert has to hold, right? That if I started with x and equal to 1 and y equals 0 at the beginning, then when I'm done, I better make sure that x is greater than or equal to y. So these are verification conditions that are actually generated by existing solvers, by existing analyzers. And surprisingly, if you were to sort of take a well-understood, state-of-the-art solver, interpolating solver, like Spacer, it fails, right? It times out. So I give you these equations, and I ask a solver to figure out what the value of p is. It can't do it, right? And it's not surprising, right? Because there's recursion here, right? There's some property that requires us to understand the relationship of this this recursive call that requires us to build an induction principle around what p is doing, right? So imagining that you can do that with just the information that we have here is a fairly tall order. So we solve this in less than a second, right? For what it's worth. So our tool, with just this information, and no inputs, surprisingly, or no sort of random testing provided inputs, just using Z3 as sort of a test generator can solve this problem in effectively 0 time. So what is the idea? So the idea, just as we said in the previous example, in the previous instance, is going to be based around learning. So the first thing we have to do is figure out how to sample data. So in this particular case, we're going to sample inputs. The important thing to note is that these samples are internally generated to our tool. It's not like we actually have to run the program or I expect the user to provide these samples or expect some kind of test generator to provide it. We're just going to use existing theorem provers to sort of generate examples. So think of these as counter-example generation, except they're not counter-examples, they're just examples. And we'll sort of generate random data in this way. And when we do, conceptually, what we've got is a table, right, of positive and negative samples. And just as we did before, our goal is to try to find a classifier that can separate the circles, which are the negative instances from the pluses, which are the positive instances, right? So what do I mean by positive and negative here? So the one cheat that I'm making, that difference, that sort of differentiates what we had before, is that I have this assert, right? I do have something to hold on to here. It's not like I'm imagining what positive and negative means, out of thin air. We have an assert. And so we're going to use that as an anchor to sort of figure out what we mean by positive and negative here. And so we can imagine that when we run this particular program, we get these kinds of inputs and outputs. So the y-axis represents y, the x-axis represents values of x. Okay. So using a very, very simple classifier, just using a very, very simple classifier operating over very, very simple template features, we can imagine something that says, well, when x is greater than or equal to 1 and y is greater than or equal to 0, we can separate out the positive and negative cases, right? So, and that's our predicate, right? So as long as the predicate satisfies this particular conjunction, we're satisfied. We're done. Okay. So the question is, can we? How do we sort of take that intuition and actually turn it into a tool that can actually work for programs that are much more sophisticated than the simple program that I gave here? So here's the idea again. So the sort of workflow is, give me a collection of verification conditions that are expressed as CHCs. Use the power of SMT to sort of generate samples as a sample generator. Produce samples. Try to learn from these samples, build this classifier, and make sure that the samples that you do, the specifications that you do produce, are in fact invariants, that they're inductive invariants. That is, they satisfy the semantics of the C program that we're actually given. It falls under the sort of transition system that is defined by the meaning, that defines the meaning of what we mean by a program execution. Right. Okay. So in order to make this useful, we would imagine that we would want to go beyond something as simple as x equal to 1 and y greater than 0, right? That's a relatively impoverished domain. So our question is, can we do learning over a domain as rich as polyhedra, right? So we want to be able to reason over arbitrary sets of conjunctions and disjunctions over forms, predicates, that have this kind of form, right? Which is a much richer space than the box domain or the octagon domain.
Okay. Suresh, just a quick question. How do you know that you can generate both the positive and negative samples? If you want to have assertion violation, that's a hard problem, right?
Indeed. Right, so you don't know, right? So I'll get to that in a minute. So we're going to essentially use counterexample guided refinement for this particular problem, right? So we're going to use Z3 to essentially drive execution to try to produce inputs that from the VCs that we have that cause a violation of the assertion, essentially by negating them in various ways. But I'll mention that in just a minute. Okay, so here's a slightly more complicated program. The program in and of itself isn't that interesting, but just as we had before, there's a loop invariant that governs the behavior of that while loop, and our goal is to try to discover it, right? Except that when we do sampling, and for the moment, to just assume that I can generate these negative samples, we get a graph that looks much messier than we had before. Right? There is no simple linear classifier that separates out the positive and negative samples. And indeed, the actual classifier is nonlinear. It has this very, very funky shape that is unclear how we could actually generate just using the feature space that we had. So if we tried to just apply off-the-shelf tools that try to construct classifiers, linear classifiers, like SVM, perceptron logical, logistic regression, it's going to be a problem because those tools are in the business of trying to maximize generality, even at the cost of soundness. That is, they're okay mislabeling certain inputs. Right? They're okay mislabeling a positive sample as a negative sample in the quest for generality. Right? That's the whole name of the game in machine learning. Right? Whereas we, in the sort of field space, we're not interested in generality, or we would like generality, but we're much more interested in soundness. We can't afford to tolerate a misclassification. So we have this tension. We have generality on the one side, which is given by these tools, but we want safety, which is sort of paramount to us. So how do we sort of reconcile that? And so, just as we did before, the technique that we're going to apply is extraordinarily simple. Rather than trying to assume that we can generate a single classifier, maybe there's a collection of classifiers that collectively discharge the properties that we want. And as long as we can construct that collection, and each of these classifiers individually sort of fits the polyhedral question that we have, now we have a way of building a sort of conjunction of possible classifiers, and we can use that as the property of the invariants that we want to construct. So that's what we're going to do. So we can imagine that we will call an off-the-shelf tool to sort of generate the classifier for us. And when we do that, we might get back a classifier that looks something like this. So it generates, it's able to separate a number of positive samples, but it mislabels a bunch of other positive samples. The 3 samples on the top over there, on the top of the line, are mislabeled, right? So we can run the classifier again, trying to classify those positive samples. That is, we can ask, can you come up with a classification that separates all of those 3 positive entries on the top of the blue line from all of the other negative entries on the top of the blue line. And when we do that, we might come up with something like this, right? So this classifier correctly classifies the 2 entries on the top of the blue line, misclassifies the entry on below it, but we can repeat, right? We can repeat the same strategy. And so now we can ask, can I construct a classifier that does that? And this classifier that we produce correctly separates out the positive sample from the 3 negative samples on the top, but unfortunately mislabels a bunch of the negative samples, right? One more time, and when we do that, we essentially end up with a specification that collectively separates out all of the positive and negative samples, right? So it's a really simple idea, right? But it requires us to observe that we can, through an iterative process, essentially refine the degree of mislabelings that we actually have that's provided by these classifiers. So there are a bunch of questions that you can ask. How do we know this will terminate? Is it actually true that if we run this enough times that we can actually construct this separation? Are there limitations on the kinds of structures that we need to do? So I'll get to all that in a minute. But surprisingly, this particular strategy works for all of the benchmarks in SVComp. So the 700-odd benchmarks in SVComp all sort of satisfy this particular extraordinarily simple approach, right? So let's see. So there are a bunch of issues that I've glossed over that are worth thinking about. So here's another slightly different program. And if I run the same strategy, run the same algorithm, I get a shape that looks like this. And so forgetting about what the program is doing, just looking at this graph, the blue line represents positive samples, the red bars represent negative samples, and they're all mixed up together. It's not very clear what the sort of separation is. And indeed, if I run my logistic regression tool on this, I get a bunch of classifiers, and those classifiers don't look sensible, right? It has stuff like 249 minus 17x plus 6y greater than 0. So ignoring the issue of whether this is actually verifiable by Z3, just as a human, it's sort of bizarre because there's no 249 sitting in the program, but the classifier seems to believe that that's a valid classifier. So the very first thing we need to do, and indeed, if I were to run this, if I were to take this classifier and then try to verify that this is sound with respect to what we've got, Z3 barfs. It says it doesn't know what's going on, right? Not surprisingly. So can we actually generalize from what we have to real invariants? And indeed, we use decision tree learning for this particular purpose, so we can actually use other tools available to us to construct simpler classifiers, and I won't go into the details of what decision tree learning is, but it's again off the shelf. So I'm not a machine learning guy, but the machine learning guys have been able to do good work with decision trees, so we can take off the shelf tools to actually produce a classifier that eliminates all of the spurious or all of the unnecessary classifications to come up with a much simpler form that we can then indeed verify is sound with respect to what Z3 tells us. Right. Okay. So the whole idea here is that as we generate our programs, right, we want to make sure that things are inductive. And so we have recursion. This complicates things. So we want to make sure that our postulated invariance satisfies an inductive property that can be used for automated verification. And our trick, or the way that we're going to do things is we're going to consider a particular sample or a particular predicate as being valid if it's reachable from, or if it's explainable from existing positive predicates that we've already discovered. So if I can reach, or if I can derive a particular classification from existing classifications, then I'll accept it. If I can't show that, then I'll reject it, right? And so all of these different pictures here are sort of explaining that graphically. Right, so how well does this work? So we ran a whole bunch of experiments trying to see whether this system actually does what we claim it does. So here's one particular graph. This is comparing against Spacer. And so the way to interpret this graph is the x-axis represents the amount of time that it took for Spacer to run. The y-axis represents the amount of time that it took to verify the particular programs in question by our tool. So higher is bad in some sense. It's sort of a reflection of time. So Spacer seems to run really, really fast compared to what we can do. So that's unfortunate. That's a bad thing for us. But on the other hand, all of these things over here represent cases where Spacer times out, where it was unable to find a solution to the loop invariance that we were interested in discovering. And if you see on the top, there were very few cases where we were unable to actually discover a verifiable invariant. So the upshot is, indeed, Spacer and these kinds of static tools can be faster than us because we're not actually generating counterexamples and doing things like that, but we tend to be able to verify more programs. And indeed, we've looked at a bunch of different implementations, and our particular tool seems to be much more robust in being able to verify these kinds of complicated loop programs and existing mechanisms. And indeed, we looked at 679 programs, several of them, or a number of them, over 10,000 lines of code, and the overall time, by and large, on average, for us to verify or to generate a loop invariant is less than 13 seconds. So this is actually within the scope of real usability. Just one other comparison, and then I'll stop. We also looked at the question of comparing us against template-based or synthesis-based strategy. So you can imagine that we can synthesize this loop invariant by having templates and sort of filling in these templates. And Pi, which was a tool that was presented in PLDI 16, does exactly that. And here, we actually do much better. We have the same degree. We have the same degree of ability to generate invariants, but the time it takes for us to actually do it seems to be substantially better than what Pi was able to do for at least the benchmarks that we looked at. Right. Okay. So two things. So in summary, it looks like this kind of learning-based strategy where either you use tests that come from the outside to actually generate, to postulate invariants and then verify them post facto, or use Z3 to sort of generate samples for us and leverage classifiers, off-the-shelf classifiers to construct loop invariants. Both of these strategies seem to be quite productive, quite valuable, and it looks like we can actually integrate this inside of a full verification pipeline. Given all of this, the question is, are we done? Is there more to do? And it's intriguing to imagine whether we can actually generalize these kinds of ideas for other kinds of properties. So 3 properties that we're actually looking at now is, so suppose that we looked at a richer class of specifications beyond just specifications that are drawn from polyhedra, combinations of linear inequalities, or containment, ordering properties? Can we actually look at separation logic, for example? Heap manipulating programs where we actually have effects. Can we actually use learning to actually generalize a formula that can be used to verify the behavior of heap manipulating programs? We've actually been able to produce applied the same strategy for discovering learning protocols. So one of the things that we would like to be able to do is, given a distributed protocol, can we actually construct an inductive invariant that captures the meaning of that protocol? And we've been able to apply the same technique for that. And I think at that point we're talking about synthesis as a general mechanism for being used, but that can be exploited using this kind of learning technique. So,
right, thank you. Over time, so any questions? Yeah.
Right. So Suresh, so suppose the program, the verification needs to go through needs a nonlinear invariant, right? You're doing linear classification, you generate all these points, you can do the classification, and then you fail, right? So you repeat?
Yes.
Okay.
Yeah.
More questions? So I had one quick question on the features. So do you fix the features, but there's no like a loop going around like looking for better features and trying to learn the features? So
in what I've described, no, but that's part of the actual tools that we can produce, right? So you can generalize over the features that we have. Mm-hmm. In the ML case, the features are fixed in some sense, right? They're drawn from the shape of the data types. They're specialized to the data types that we have. In the loop invariant case, the features aren't fixed, right? It's anything that's drawn from polyhedra. So the actual shape is arbitrary.
Mm-hmm. Okay, so let's thanks Suresh again.